So the first thing we need to decide is whether we're going to have, thanks, Tom, the homework due Wednesday as stated on the web. So is that all right? I know one person's already turned in an assignment.
Can we wait till Monday to decide?
Okay, is there a second? All right, we'll wait till Monday, but let's not push things back too much, because the way you learn is by doing homework. And we don't want to make it too easy. So let me first of all review some of the things we learned last time. I'm going to use yellow chalk for the review part. Okay, so that's the fundamental commutation relation for angular momentum. Since J is a vector, J dot J is a scalar, and so it's inert under rotations. We defined J plus or minus equal to J1 plus or minus I J2. We saw that J3, J plus is equal to H bar J plus. And in fact, we can compactify this by saying plus or minus, plus or minus, plus or minus. We also found that the commutator of J plus with J minus was 2H bar J3. As usual, asking questions is an important part of the learning process and the teaching process. So if I start asking questions, the idea is for you guys to ask the questions. We found that J plus J minus is this, and in the opposite order, it's a similar structure. Okay. And by adding these two together, we found that J squared was equal to a half J plus J minus plus J minus J plus let me just say, plus J3 squared. There. I noticed last night in my notes that, looking over my notes, that I really could have said something a little bit clearer about some of these things. In any event, we found that J dot J in any state psi was greater than or equal to 0. So that means that if Jm is an eigenstate of J squared, then, whoops, let me do that a little better. Then if psi is equal to Jm, then this is greater than or equal to 0. And so if in particular J squared Jm is equal to alpha Jm, then this is equal to alpha, which is greater than or equal to 0. We decided to set alpha equal to J plus 1, H bar squared with J greater than or equal to 0. And that's the way we proceeded. And we then considered J squared on Jm, H bar squared J plus 1, Jm, and J3, Jm equal to h bar m Jm. So these are the two equations that we set out to analyze with the aid of these equations, which we derived from the fundamental angular momentum commutation relations. And we found various things about these. In particular, we found that m had to lie between minus j and plus j. And then we found that by considering the norm of j plus on the state Jm, assuming it's an eigenstate of these two variables, these two quantities, which of course commute, because this is a scalar, j3 commutes with j squared. We found that this was equal to h bar squared j minus m j plus m plus 1, and that has to be greater than or equal to 0. And we also found that j minus on jm, which here we use these two equations and then factorize the resultant expression. And this turned out to be j plus m, j minus m plus 1. That's greater than or equal to 0. So we have these two inequalities. And this told us that m can't exceed j, and m can't be less than minus j. And so that proved this relation here. Any questions? I do have, here, I forgot to pass out the crackers. I don't know who wants to take the crackers. Here, let me toss them to you. I also do have still some, a little bit of chocolate as a reward to anybody who has a question. Chocolate I picked up at a Japanese restaurant. Okay, so this particular relation here, this bottom one here, tells us that if m is equal to minus j, then this expression is 0. And so that told us that the j minus on the state j minus j was just equal to 0. We also knew, of course, that j commutes with j minus, and we used that to show that j squared on j minus jm was equal to h bar squared j plus 1 j minus on jm. And that tells us that this state is an eigenstate of j squared with eigenvalue h bar squared j plus 1. So in other words, when you act with j minus, you don't change the eigenvalue of j squared, because j minus commutes with j, and that's because j squared is a scalar. We then showed that j3 on j minus jm was equal to h bar m minus 1 j minus jm. So that tells us that this state j minus jm is an eigenstate of j3, but not with eigenvalue mh bar, but with eigenvalue m minus 1 h bar. So it's one down. And so that's basically the review of last time. Any questions about that? Or about anything else? More is relevant to physics. Okay, now we want to fool around with j plus. So the first thing, I guess, is to go back to this expression here and show and see that if we set m equal to j, then we get 0. So that tells us that j plus, I should start with the white chalk now, I guess, since we're no longer reviewing. J plus on Jj is just equal to 0. Which is, in other words, you can't lower the state J minus J, you get 0. You can't raise the state J. And that's just by plugging m equal to J in this equation, this term gives you 0. The next thing is that, of course, J squared commutes with J plus, because J squared is a scalar, and so that applied to the state Jm gives us, again, we're always assuming these two equations. And then this gives us J plus J squared Jm. What am I doing here? I somehow skipped something. Yeah, I skipped something. This is certainly 0. So now what we can do is we can say J squared on J plus Jm using this commutator is equal to J plus J squared on Jm. And J squared on J plus Jm by this equation is H bar squared J plus 1 on Jm. So that tells us, whoops, sorry. So that tells us that the state J plus Jm is an eigenvector of J squared with the same eigenvalue as any of the other states. So J plus does something to Jm, but it doesn't change the eigenvalue with respect to J squared, just as J minus did. Okay, the next is to use the fact that J3 J plus is H bar J plus. And then we apply that to the state Jm, and we get J3 J plus on Jm is equal to H bar J plus on Jm. And so this gives us J plus J3 Jm is equal to J plus J3 Jm plus H bar J plus Jm. Well, J3 on Jm by this equation is J plus H bar M Jm, and this is plus H bar J plus Jm. And so this is just clearly H bar times M plus 1 J plus 1 Jm. And that tells us that this state is an eigenstate of J. Oh, I did it backwards. What did? No, I wrote this backwards. The thing was right, but I wrote it backwards. Right. This is the commutator. So the first term is J3 J plus minus J plus J3, and I put that term over here. And so the state J plus Jm is an eigenstate of J3 with this eigenvalue, in other words, 1 up. Okay. So now we've learned a lot about these states. And we're almost done. We know that M has to lie between minus J and J, and consequently we can set M equal to J minus X, where X is non-negative. That will satisfy this relation, and we can say M is equal to J minus J plus Y where y is greater than or equal to 0. And that gives us this relation. Of course, we don't want to make x and y too big. But now if we add them together, we get that 2m is equal to x plus y. But before doing that, again, I skipped ahead in my notes here. Before doing that, what can x and y be? Can they be imaginary numbers? No, because the eigenvalues of a Hermitian operator are real, so they have to be real numbers. So could they be something like 1 over root 2, or even something as common as 1/2? Well, if x were 1/2, suppose x were 1/2, then, for example, we could look at this equation, which says J3, J plus Jm is equal to h bar m plus 1, J plus Jm. And if we apply that, say, to the state J, say x equal to 1/2, this would then be J3, J plus J, J minus 1/2 equals h bar, m is J, so this m is J, minus 1/2 plus 1 would be J plus 1/2, J plus J, J minus 1/2. But this would say that there's an eigenstate, namely J plus J, J minus 1/2, of J3 with an eigenvalue here. In other words, m equal to J plus 1/2, which is greater than J. But that would violate the rule we found over here. The bounds on m. So that tells us that x couldn't be, say, 1/2, or any fraction like that. What about if x is an integer? Well, if x is an integer, it's okay, because, for example, if we wouldn't get into a contradiction if we had, for example, m equal to 0. I mean j minus 0, because then we'd have j plus on jj is 0, and that wouldn't get us into this problem. If we instead had x equal to, say, minus 1 instead of minus 1/2, then this would have gotten us simply to h bar j, and we would have raised the state j minus 1 just to the state jj by using j plus. So what this tells us then is that x and y are integers. Now when we add them together, we get that 2m is equal to x plus y, but more importantly, let's write these equations slightly differently, namely j is equal to m plus x, and j is equal to, or minus j is equal to m minus, let me get that right, minus j is equal to m minus. I want j. J is equal to minus m plus j. All right. I should really recurse it better. J is equal to minus m plus y. Adding the two together, we get 2j is equal to x plus y, which is then an integer. So j is equal to an integer divided by 2. And this, of course, is the really surprising result that comes out of this analysis. This result is really not, it is a result in quantum mechanics, but it's also a result in Lie algebra theory. And if we had been doing this simply from the point of view of group theory, we wouldn't have introduced H bar at all. We only introduced H bar because we wanted to have the operator that generates rotations the e to the minus I theta dot j angular momentum, and so we had to put in an H bar to make this thing dimensionless. If we were studying this thing purely as a Lie algebra thing, we would have had this be e to the minus I theta dot, just the ratio of these two, which we would have called, let me say, script j. And then we would have gotten the same result for eigenvectors of script j squared and script j3, namely that j had to be an integer over 2. And so the possibilities then are 0, not only an integer, but a non-negative integer. So I should have said non-negative. So the possibilities are 0, 1/2, 1, 3/2, 2, and so forth. And the cases where you have 0, 1, 2, 3, these things are called bosons, at least if they're elementary particles, or if they're just systems where the total angular momentum is, the total J quantum number is 0, 1, 2, or 3, or whatever, those are bosons, and then these guys are fermions. And as you know, there are radical differences in the properties of these two kinds of systems. Bosons are like sheep, the fermions are like cats. The bosons like to huddle together in the same state, but the fermions have to be in antisymmetric states, and therefore obey the Pauli exclusion principle. So we've seen the values of m run from minus j to plus j in integer steps. Integer steps because is what we saw over here, namely that we lower by 1, or over here we raise by 1, so those are certainly integer steps. And so m, the values of m differ from j by an integer, and j itself is, as I said, a non-negative integer divided by 2/2, a non-negative integer. If you count up the number of possibilities, then if you have one state, and now let's think about a state, a quantum mechanical state that has some other quantum numbers, and then j, and then m, there will be 2j plus 1 of these states, which you can start at the top one, jj, and then you act on that with j minus on jj, and that will be some constant times j minus 1, and so forth, and then you can go all the way down to the state j minus j. And altogether there are then 2j plus 1 of these states. So if it's j is 0, there's only 1. If j is a half, like for the electron, simply the spin part of the electron, then you have 2 states, namely 1/2 and minus a half. If you have a massive vector particle, then you have j equal 1, and you can have j equal 1, 0, or minus 1. All right, now a little bit about that normalization. We saw, well, let's just write this down. J plus Jm is then some constant times J, m plus 1. So what's the constant? Well, Jm, J minus J plus Jm is going to be absolute value of c squared times Jm plus 1, Jm plus 1. But these states we're going to take to be normalized And so this is just equal to c squared. On the other hand, this thing is equal to j minus j plus. We have that written somewhere here. J minus j plus is j squared minus j3 squared minus h bar j3. And so when we substitute that in here, we have jm times j squared minus j3 squared minus j3. And minus plus is minus h bar j3 jm, and that's equal to jm h bar squared j plus 1 minus and h bar minus what am I doing here? Minus, this is squared, sorry. So this is minus mh bar squared, and then this one is minus m h bar squared jm. And altogether that's h bar squared jm times j plus 1 minus m plus 1 jm. The state jm, though, is assumed to be normalized, so this is h bar squared times j plus 1 minus m plus 1. And people usually factorize this, or rather, well, actually they leave it that way. So somehow that's the way it is. Okay. So this c, in other words, is the square root of this thing, and conventionally we take the positive square root. So j plus 1 minus m plus 1. Okay, so that's the expression. In other words, this is equal to h bar square root of j plus 1 minus m plus 1 times j m plus 1. So this is one of the key equations that goes into finding these coefficients, which are called, they're named after Clepsch and Gordon. Unfortunately, very few people can spell Clepsch, and I'm not one of them. So I'm not going to spell Clepsch for you. But anyway, so we have this basic rule then, is taught convention, h bars. Well, remember, you might say, well, what's this about a convention? You remember the overall phase of the quantum state isn't measurable, so we're allowed to have certain conventions. And this one is universal. Not all the conventions having to do with angular momentum are universal, though. All right, so that's that, and if we take then the inner product of that, which is state jm plus 1, we get j plus jm like that, is just simply h bar times the square root. Again, we're requiring that the states are normalized. So in other words, deriving this rule and some of the other rules that I'm about to derive, deriving it, I'm assuming that all the states are normalized. If they're normalized, then this is what it is. If instead this state has norm 3 and this has norm 36, then clearly C has to be something a lot different from what I wrote down. But it's a universal convention that they're normalized. If we now take the complex conjugate of this equation, we get Jm J minus J m plus 1 is the same thing, h bar square root of J plus 1 minus m plus 1. But normally we like to have what J minus does on the state Jm, so we subtract 1 from m in this equation, and we get J m minus 1 j minus jm equals h bar, and the square root changes to, well, it's factorized now, j minus m plus 1, j plus m. And in fact, if I factorize this, then this is h bar square root of j minus m, j plus m plus 1. And for that matter, that's the same thing as this, because this is a complex conjugate. So equals ditto, and this is a bounded ditto. Where this is equal to. All right. Now, in fact, when we have this equation here, we see that this state j minus jm we know is an eigenstate of J3 with eigenvalue, in other words, J3, J minus Jm is equal to H bar m minus 1, J minus Jm. And so this state is orthogonal to all the other eigenvectors of J3 with different eigenvalues. And so we can simply write J minus on Jm is equal just to H bar square root of J minus m plus 1, J plus m, just times the state J m minus 1. So that's basically the last equation of this set of equations. All right, well, this was all very mathematical. As I said, it's really part of Lie algebra. Let me once again invite questions before I start a new topic. All right, the new topic is to make some contact with the sort of, with spherical coordinates and with the sort of formalism that we would use for discussing Schrödinger's equation for the hydrogen atom or for any central potential, spherically symmetric potential. Potential spherically symmetric, and of course, what we want is to use spherical coordinates. All right, well, a change in position, dr, is going to be in rectangular coordinates. It's x hat dx plus y hat dy plus z hat dz. Hat means unit vector, so this just means x hat times x hat is equal to 1. Okay, this thing we can also write, though, as r hat dr plus r theta hat d theta plus r sine theta phi hat d phi. So that's the idea in spherical coordinates. We've got the x-axis out here, y-axis there. This is the z-axis. This angle here is theta. If you drop this down to the xy plane, then this angle is phi. And r hat then is a unit vector that points this way. Theta hat is a vector this way. And in fact, it's a vector in the direction of increasing theta, and phi hat is what happens when you increase phi, and so phi hat is into the board. Well, not quite into the board, sort of that. Okay, now I'm going to write r hat, theta hat, and phi hat in terms of x hat, y hat, and z hat. And I guess I'm just going to, I'm not going to derive these, but they're certainly plausible. Sine theta cos phi plus y hat sine theta sine phi plus z hat cos theta. Theta hat is x hat cos theta cos phi plus y hat cos theta sine phi minus z hat cos theta, and then phi hat is minus x hat sine phi plus y hat, well, might be better than that, y hat cos phi. Okay, so you see here that phi hat, since it points that way, is perpendicular to z hat, so there's no z hat component in phi hat. You see that these three vectors are all these are an orthonormal triplet. What can I say? This is in fact this quantity here, for example, is the x component of r hat. This is the y component of r hat, and this, of course, is the z component of r hat. I'm talking about the magnitude here. And the same thing for theta and phi. Theta and phi are a little bit harder to figure out, but this is basically the rule. Okay. Any questions? You want me to try to justify this a little more, or shall we just move on? Okay, the inverse relations can be obtained by just saying, for example, that x hat is equal to x hat dot r hat times r hat plus x hat dot theta hat times theta hat plus x hat dot phi hat times phi hat. So that's pretty clear that in other words, just as x hat, y hat, z hat form a basis, so do r hat, theta hat, phi hat, and so those are the components. Well, if we just calculate this by forming the dot product of x hat with r, well, x hat dot r, the only component is the first one, so that's just sine theta cosine phi. And in this way, what we find out is that x hat is equal to sine theta cos phi r hat plus cos theta cos, that's supposed to be cos phi, cos phi, theta hat, and then minus sine phi, phi hat, and then y hat is equal to sine theta sine phi r hat plus cosine theta sine phi theta hat plus cosine phi phi hat. So this is just taking the dot product of y hat with all these, with theta hat and x hat and theta hat, r hat, and phi hat, and so forth. Similarly, z hat is equal to cosine theta r hat minus sine theta theta hat. This one's the easiest one because we take, we have here z hat dot r gives us this one, z hat dot theta hat gives us this one, but z hat dot phi hat is 0, so that doesn't. Okay, so this is the basic geometry. Now let's go on and add a little bit of calculus. Let me get a so the gradient, let me go over here. The gradient operator is defined in this way. dr dot grad f is the change in f, and the change in f is certainly dr times partial f partial r plus d theta times partial f partial theta plus d phi, change in phi, times partial f partial phi, that's for sure. But then that must mean that this is dr dot, and dr is over there. It's r hat dr plus r theta hat d theta plus r sine phi plus sine theta d phi times phi hat. You need phi hat dotted into grad f. And so what we see here is that grad f then is equal to r hat just partial r plus theta hat. Now with theta hat, the part that's theta hat, there has to be a piece that cancels r in order to just give us this. So it is 1 over r partial theta, and then plus phi hat, and then 1 over r sine theta partial phi. That's to cancel this term. So that gives us what the gradient is. And so the gradient operator by itself, in fact, that's what I'm sorry, that's all of this times hat, but the gradient operator by itself is what's inside in fact, if I use the shorthand, then it's theta hat over r d theta plus phi hat over r sine theta d. So is this notation all right? That d sub partial symbol, so r means this, and partial theta means that, and partial phi means that. All right. Okay. Well, we know that the angular momentum is r cross p, and if we have a state here r, and this is L, and then an arbitrary state, so this is a position eigenstate, then in this case, what we would have is this is r cross p psi. This is r operator, this is the eigenvalue, so this becomes the eigenvalue cross r p psi, but p is represented by h bar over I times the gradient, so this is h bar over I r cross, and now the gradient operator. I'm going to write the gradient operator. Well, let me just write this gradient operator first. And so r psi is what we would call the stationary state wave function. for the state psi. This really eats up Blackboard. Can you guys see if I write here, if I read this line, can you guys see, or is this too low?
That's fine.
You can see, Sid? I mean, can you see? All right. So what this is h bar r, length of r, over r hat cross, and now I'm using the gradient here. And the gradient is r hat partial r plus theta hat over r partial theta plus phi hat over r sine theta partial phi, all of that acting on the wave function. Okay, so let me just repeat for one person who was out of the room for some reason. We inferred by this argument that the gradient was this in spherical coordinates. We let L equal R cross P. We take the matrix element of L. We pull out the R. It's an eigen. This is an eigenstate of R, so this just pulls out an R. P is represented by h bar over I grad, and then I just write the gradient in spherical coordinates. But now, R hat cross R hat is 0. R hat cross theta hat is phi hat. And R hat cross phi hat is minus theta hat. And so this is equal to h bar over I. Moreover, we have this R cancels these two R's. So there's a lot of simplification here. This becomes simply phi hat partial with respect to theta minus theta hat over sine theta partial with respect to phi, all that acting on the wave function R psi. Okay? So that's what L is. RL psi is just this in spherical coordinates. And that kind of makes sense because it is something that just involves changing the angles. And it's kind of nice that it's an expression without any R in it. That's what you sort of intuit, but when you look at it as R cross P in rectangular coordinates, it doesn't look like this at all. All right, now we want to go a little bit further with this, but if there's a question, remember, I do have chocolate to reward questions, so if there are any questions, and what kind of chocolate doesn't count as a question. All right. If any of you guys understand why nobody asks questions, I wish you'd explain it to me after class. And by the way, as far as office hours are concerned, anytime you see me, you can come up to me and ask me a question. And I'm around afternoons and evenings. All right. What about, so this is the whole picture for L. What about just LZ? Well, R, LZ, psi, this would be R, Z hat dot L, psi, and so this is equal to Z hat dot h bar over I, phi hat d theta minus theta hat over sine theta. Sorry about writing so small, but this is the wave function. Okay? That's invisible, I guess. Now what about z hat dotted into these things? Well, z hat dot phi hat is 0. Z hat dot theta hat is minus cosine theta. Wait a minute, minus cosine. I have that right, let me just make sure, because yes, this is wrong. I made a mistake here. Somebody should have told me on this. This is a sign. So z hat dot theta hat is minus sine theta. And so this is simply the z hat dot that is minus sine theta, so that cancels. So this is just h bar over I d by d phi of r sine. And that's something you've probably seen before. The components of Lx and Ly are a little bit more complicated, but this isn't deep stuff. It's just a question of using all those geometrical relations in a logical way. And so you should work through this on your own, because I think I will assign some sort of homework, second homework assignment for this. So let's look at R, Lx, sine. Well, of course, this is just R. No hat. I don't know why I did that. And of course, this is x hat dot h bar over I phi hat t theta minus theta hat over sine theta d phi on r sine. Okay, well, what is x hat? Well, let's just put the h bar I out there. X hat, using that top equation over there, this, and notice the only part of x hat that we need here is, let's see, I didn't use the r hat part. Oh, I didn't use the r hat. Let me see here. Right, I didn't use the r hat part because the r hat part is perpendicular to these two. So all I need here is cosine theta, cosine phi, theta hat minus sine phi, phi hat, all that dotted into this, which is then phi hat d theta minus theta hat over sine theta d phi, and we can call this psi of r just as well, right? It's a little bit easier to write. And now we're just taking this dot product, and so theta hat gives a non-zero component here, and these two give a non-zero component. The rest of it's zero, and so this is just h bar over I minus sine phi d theta minus cotangent theta cos phi d phi times psi of r. So that's an expression that I know the first time I saw this or an equivalent expression, I thought, gee, that was pretty weird. Where the hell did cotangent come from? But we see it comes out very naturally because we've got a cosine and a sine, and theta the hat dot theta hat is 1. So that's where it comes from. Okay, we can do the same thing with Ly. Let me start down here. R hat Ly psi is then, let me just skip a step and pull out the y hat. Is y hat dot R L psi. So this is y hat, or better yet, let me pull out the h bar over I. H bar over I, y hat dot, and then the angular momentum part here is just this structure here, phi hat d theta minus theta hat over sine theta d phi on psi of r. And now we have to look up what y hat is. Well, y hat has a component involving r hat, but that's irrelevant because it's perpendicular to these two. So we just take the theta phi components of y hat, and that gives us h bar over I cosine theta sine phi theta hat plus cosine phi hat. It's very hard to write with this chalk when it's too low. And then just phi hat, this old thing. Phi hat d theta minus theta hat over sine theta d phi. Again, on this, just call it psi of r. Okay, now taking the dot product, we get a component from that and a component from this, and the rest is 0. Cross terms is 0. And so that gives us that R Ly psi is h bar over I cosine phi d by d theta minus cotangent theta sine phi d phi on r psi. I put back r psi because we have r psi over here. All right, so that's what Ly is. Now you remember when we did this analysis of the basically the Lie algebra angular momentum, we didn't use of course x, y, z here over here went into 1, 2, 3. I didn't mention that explicitly, but I assume you realize that. You notice that we used J3, but we didn't use J1 and J2, which would be Lx and Ly here. Instead, we formed these complex linear combinations, J1 plus I, J2. So too here, we'll be talking about L plus and L minus, and it turns out they have a simple form. So let's look at L plus or minus on the side, which is to say R Lx plus or minus I Ly psi. Well, just combining, where is it? This formula with that formula, what we get, and let's see, we're getting things a little bit. Okay, so R L plus or minus I is h bar over I times minus sine phi plus or minus I cosine phi d by d theta minus cotangent theta cosine phi plus or minus I sine phi d phi I guess I do need a big bracket here. And I'm just going to write this as psi of r. All right. Well, you can see that this part here is just e to the plus or minus I phi, which should ring a bell from the elementary quantum course. This one you need to massage a little bit. And when you do, what you get is h bar over I, e to the plus or minus I phi plus or minus I d by d theta minus cotangent theta d by d phi on R psi. Okay. All right. Frankly, the way to, so this part is pretty easy to do from there to there. This one is more confusing because you have to factor out an I, or plus or minus I. And if you do the plus case, then you can see that when you factor out the I, to get this minus sign, you need, what's left is cosine phi plus I sine phi, and that gives you the even plus I phi. With the minus case, we put in minus I. Just do the arithmetic explicitly at home, and you'll see that it works. All right. Well, that's a surprisingly simple expression, given that there were other expressions more complicated. That, namely, that R L plus or minus on psi is e to the I plus or minus I phi h of R over I, and then this d by d theta with a plus or minus I and then minus cotangent theta d by d phi. So it's reasonably, it's simpler than one could have expected. Now, we have this general relation that j squared is a half j plus j minus j plus j3 squared. So we have the same relation for L squared, namely that L squared, the vector, it's not written very well, but I guess you know what I mean, is a half L plus L minus L plus L3 squared. And one can then show that R, in fact, I think I'll make this a homework problem. R L squared psi is equal to minus h bar squared 1 over sine squared theta d. I'm just going to kneel down. D by d phi squared plus 1 over sine theta d theta of sine theta d theta, all that acting on R psi. Okay, so that's the angular momentum part. This thing is d phi squared. That's what that means. And the way to find that out is to use this formula, that equal to this, and also use the formula over here, namely the formula for LZ. What the hell is that that's over here? Use this expression. So, I'm going to make that a homework problem. Any questions? All right, so let's see. Let me use this board for one last part. While I'm erasing it, I'll tell you a story presumably most of you have heard. When Gandhi, the Indian politician, visited England, one of the English journalists interviewed him. I think it must have been the days of radio, so this was a radio, maybe a print journalist or a radio journalist. Said, Mr. Gandhi, what do you think of European civilization? And Gandhi replied, I think it would be a good idea. I think that's very funny. Evidently quick on his feet. Okay, well, I hope I've got enough space here. Grad squared, which, by the way, is often written as simply a triangle, just to make things, it's just a notation that makes things a hell of a lot easier when you save a little bit of chalk. sum I equal to 1 to 3 partial 2 partial x pi squared. That's the thing in rectangular coordinates. Now, I'm going to just take for granted that in spherical coordinates, that's 1 over r squared d by dr, r squared d by dr, plus d by d theta, sine theta, d by d theta, divided by sine theta. Now this, I should have written this a little bit differently. Let me put the plus 1 over sine theta. So this sine theta is to the left of all the d by d thetas. And then plus 1 over sine squared theta, d by dt squared. So that's what the philosophy is. By the way, I put a link on the 522 webpage to my class notes that I developed for 466, which are in the form of a huge PDF form. And so those of you who are curious about more about Lie algebra can go to chapter 2 in that, or group theory. You can go to chapter 2 and read about that. You can also, if you want to find out more about Laplacians and spherical coordinates, or you can go to chapter, I don't remember what it is, chapter on tensors. It's a mixture of tensors and general relativity, and you can look in there for a derivation of this expression, or you can find it elsewhere. Okay, so what is r p squared? Because this is, of course, what enters is the essential part of the kinetic part of the Hamiltonian for a single non-relativistic particle. And this is clearly minus h bar squared grad dot grad of r psi, or equivalently minus h bar squared Laplacian psi of r, which is another way of saying it. And however you write it then in spherical coordinates, it's minus h bar squared over r squared, and then this huge expression here, d by dr, r squared d by dr, plus 1 over sine theta, d by d theta, sine theta, d by d theta, plus d by dt squared over sine squared theta on r psi. Now, if you compare this with what we've got over there, you can see that this is equal to minus h bar squared over r squared d by dr of r squared d by dr of r psi plus 1 over r squared r L squared psi. So this takes the essential part of the kinetic part of the Hamiltonian, gives you an expression involving r, and then an expression 1 over r squared, the matrix element of L squared. And so, of course, if you are in a state, and of course you certainly want to do this, if your Hamiltonian is spherically symmetric, then the angular, then L will commute with H, L squared will commute with H, and you can simultaneously diagonalize both H and L squared. In that case, psi can be a state, we call it Ln, since it's angular momentum, the orbital angular momentum. And then this would be, in that case, this thing would be, I'm trying to find space here. Let me just do this. It would be ditto, and then plus h bar squared L plus 1 over r squared, just simply times r sine. So in other words, all this angular part, all the complexity of the angular part is just gone. It's just in the form of h bar squared L plus 1 over r squared, and then you have the derivatives acting on the repulsions with respect to r. And now the angular part of this doesn't involve r, so you can forget about that. And so this just then becomes an ordinary differential equation in the variable r, second order. So that's second order linear ordinary differential equation. That's not so bad. I mean, it's not trivial. In fact, for an arbitrary potential, spherically symmetric, nobody's ever written down the solutions in even a series, let alone this closed form. But in some cases, these have been worked out in detail. For example, hydrogen atoms in the other cases. All right, I guess that's everything. I've gone long enough. So, are there any questions? There have been 0 questions today. That is not good. Why don't you turn the thing off? So I'll save the chocolate for another day.